Let's dive right into this explainer by locking down the single most crucial framework for Singapore's power grid. We're talking about the voltage ladder. Here's the deal. Every single engineering and regulatory decision made about this grid, from which switchgear to install to what earthing method applies, traces back to one foundational number. What voltage tier are you in? Get that classification wrong, and literally every downstream calculation is ruined. We're talking about the difference between a fault that trips safely and one that turns a substation into a massive hazard. There's absolutely zero margin for error here. So let's look at the actual rungs of this ladder. Up at the very top, we have extra high voltage, or EHT. That's your 400 and 230 kilovolts. Drop down a rung and you hit high voltage, or HV, strictly sitting at 66 kilovolts. Below that is medium voltage, MV, which covers 22 and 6.6 kilovolts. And finally at the base, we have low voltage, LV. That's the stuff coming right out of your wall socket, 400 volts three-phase and 230 volt single-phase, basically anything below 1,000 volts AC. I actually like to think of this whole setup like a high-security building's floor directory. The penthouse, well, that represents our extra high and high voltages. The ground floors are our medium and low voltages. Now, each of these floors demands a completely different key card. You obviously can't use a ground floor key to get into the penthouse, right? It's the exact same concept here. Different voltage tiers demand entirely different insulation, completely different switchgear technologies, and even totally different legal operators. It is literally the filing system that tells you which chapter of the rulebook applies. And these categories aren't just industry shorthand. They have strict statutory roots. These legal definitions come straight from the Energy Market Authority, the EMA, and they align with international standards. This dictates everything from market rules all the way down to licensing. So there's a crucial point we really need to clear up right now regarding the definition of HV. In casual conversation, engineers might toss around high voltage to mean pretty much anything hotter than a standard wall plug. But in Singapore's formal system, HV legally and strictly points to that specific 66 kilovolt threshold. It is definitely not just anything above LV. If you confuse these classifications on a regulatory submission, you could actually trigger the wrong review pathway with the totally wrong authority. Let's actually test this framework in a real-world scenario to see how you'd handle a problem on the ground. Quick check. Imagine your facility trips a fault, and your incoming supply is rated at 6.6 kV. What classification tier is that? And more importantly, who exactly are you supposed to call? Is it the EMA or is it SP Group? Well, the answer is SP Group. Because 6.6 kilovolts is medium voltage, it maps directly onto their operational boundaries. The EMA runs the energy management system for the transmission network, so that's 66 kilovolts and above. But anything 22 kilovolts and below, that falls squarely into SP Group's 24/7 distribution territory. So that 6.6 kilovolt fault is totally their legal responsibility to physically fix, not the EMA's. Now that we know who runs what, let's talk about the physical backbone of the extra high and high voltage tiers. This entire transmission system is heavily meshed and engineered around a principle called the N-1 single contingency criterion. Basically, that means the network is deliberately designed to survive the sudden, unexpected loss of any single generator, circuit, or transformer. The result? Zero cascading failures, zero instability, and zero load shedding. It's essentially an incredibly robust insurance policy against blackouts. Moving into our next section, engineering the underground, Singapore's subterranean highway. Because Singapore is incredibly land scarce, you obviously can't just string extra high voltage cables across the surface of the island. So engineers had to get creative. They went down, exactly 60 meters straight down into the earth. This incredible depth was chosen deliberately to completely remove the transmission network from the reach of virtually all future above-ground construction and even mass rapid transit expansions. Down at that 60-meter depth, they constructed a massive 40-kilometer-long cross-island tunnel system. Think of it as a dedicated subterranean highway designed exclusively to securely house these high-capacity cables, keeping them safe and completely out of sight. And honestly, the most fascinating part of this underground marvel is that it's designed with an unprecedented 120-year lifespan. By placing it so deep and building it so robustly, they've ensured this massive asset won't need to be dug up and disrupted for over a century. That's a serious long-term play. Now, depending on which rung of the voltage ladder you're on, the actual cable technology running through those tunnels shifts dramatically. For the extra high voltages, those 400 and 230 kilovolt lines, they use oil-filled, paper-insulated cables. This gives them superior insulation performance at those extreme voltages. But drop down to 66 kilovolts and below, and the network shifts over to solid dielectric XLPE cables. It's a very calculated trade-off. You get maximum insulation where you absolutely need it at the highest tiers, and lower maintenance with zero risk of oil leaks at the lower tiers. And you'll find that exact same hardware logic applies at the substation level too. Your voltage classification dictates your hardware. At the EHT and HV levels, where space is at an absolute premium, Singapore relies on gas-insulated switchgear using SF6 gas. It's highly compact and can safely handle massive fault currents. But move down to medium voltage, and the standard shifts to vacuum circuit breakers. Once again, that specific number on the ladder dictates the physical reality of the grid's hardware. Okay, so you've completely mastered the ladder. You know the exact 4 tiers, you know who operates which level, and you understand how the physical cables in switchgear change as you move up and down. But this leaves us with a pretty critical question. We know these numbers are exact on paper, right? But in the real world of electricity, nothing is ever perfectly stable. So how far is each tier's voltage legally allowed to drift before it becomes a dangerous violation? What actually happens when these exact numbers start to fluctuate? Well, that brings us to allowable voltage variations, and that is exactly what we'll be breaking down in our next explainer. See you then.